Thank you for the very, very kind introduction. And of course, I also would like to thank the organizers for giving me this opportunity to talk here in this great seminar series on input to state stability and its applications. So today's talk, I want to talk a little bit about the role or the potential of projected dynamics. So projected dynamical systems that have been around quite some time already. But I want to discuss particularly, let's say, the possibilities that projected dynamics can offer in the context of control systems. And in fact, I will do this, let's say, following this outline here. So as I said, so PDS, so projected dynamical systems have been around for quite some time. So let's say almost 50 years. So I start with a short definition, an introduction to projected dynamical systems so that you know what we're talking about. And in fact, after that, I will talk about an extension of these PDS, so an extension of this classical definition that are called, not very originally, but I called them extended PDS, that is needed in order to study, let's say, systems that have both a plan part and a control part. So that's going to be very important to study the projection-based controllers that I'm interested in the remainder of this talk. So I have two parts in this talk, and let's see, based on time, how much we can actually cover. So I certainly want to finish part one, so that's quite an extensive part, where I'm going to discuss the motivation that actually started all of this in this study of extended PDS, which are projection-based controllers, where we try to build controllers that have, let's say, the input and output sign always equal. Right, so suppose this is a certain tracking error that we have on this side, so we make sure this controller is always pushing in the right directions, which, as we will see, is a very important property that if you can induce that into your controller to overcome fundamental limitations so fundamental performance limitations that are known in the context of LTI control. Right, so I propose a very simple extension to LTI control by introducing these projection operators, but at the same time giving a lot of extra performance, as we will see. So the major part of my talk will be related to these type of projected controllers or projection-based controllers. If time allows, I want to just run by you a quite recent idea. So we just presented this at the CDC in Singapore, which is projection-based control, where we, by smart projection, can give sort of any random controller certain inherent dissipativity properties, right? So given a passive plant or a plant with a certain passivity property, if we add a certain projection to, let's say, a given controller, a rather arbitrary controller, we can induce certain dissipativity properties, making sure that the closed loop system is actually stabilized. I'm not sure if this is a cool idea, if this is relevant in any way, but somehow I like the idea. So let's see. I'm happy to hear back from you if you think that this is a useful idea or discussing how this can be extended in all sorts of directions. So in the end of this talk, I have, of course, a bunch of conclusions and also an outlook of let's say, open problems that we are currently working at. Okay, so to get going here, so to introduce projected dynamical systems, so essentially to define a projected dynamical system, I need two main ingredients. So first of all, I need, let's say, an original dynamics, which I note here. So an original vector field f dot of x, right? So these are the unprojected dynamics, right? So that can flow freely. So that's one ingredient. The other ingredient is a certain constraint set. Let me try to shortly get rid of this over here, right? So now it's gone, right? So the other thing is a constraint set, right? So I need a vector field f of x, unprojected original dynamics, and let's say a constraint set S for which I want all the states to live in. So in particular, so how is then a projected dynamical system defined? So based on this f of x and this constraint set S. So in principle, so this is very loosely speaking, I have the exact definition on the next slide, but in principle, you start from an initial condition, let's say in the interior of the constraint set S. We're flowing according to the original dynamics as long as it keeps us inside S. But at the moment that we get to the boundary of S, and we get that let's say the dynamics are pointing outside, so like here, then what we do, the projection makes sure that we project on S, in particular on the tangent cone of S, to make sure that the trajectory remains inside of S at all times. Right? So at the moment that the original dynamics are such that we remain inside S again, we can follow the dynamics again. right? So the projection operator more or less only kicks in when it's needed to make sure we have constraint satisfaction, that the state remains inside this this set S that we defined. So two important features. So all trajectories live inside the constraint set S, right? So that's the purpose of the set. Plus, you already see it a little bit from this graphical picture over here, that this projection operator induces discontinuous dynamics, right? So we have this x dot is f of x here, but at the moment we get to the boundary, you see a hard switch of the dynamics that is actually necessary to maintain all states inside the constraint set S. So this set of dynamical system has been around for quite some time, so over 50 years now. So I think this is one of the first papers, so in 1972, where I find a first variant of these PDSs being defined. And actually, they were used quite a lot in the area of economics, right? So the study of, let's say, the dynamics of certain economical systems, including prices, market, traffic networks, but also power grids, to study their dynamics and make sure that certain variables, for instance, stay always non-negative. Think about pricing or certain commodities that always have to stay non-negative. So it has been around quite some time. So, and it's quite a classical definition and received quite some time over, quite some interest over time. But what we see in recent years is that there is also, from a control perspective, quite an interest in let's say, using projected dynamics or projection in control loop. So hybrid integrators, anti-wind-up control, passivity-based control, but also online feedback optimization currently receives a lot of attention, and you see actually projected controllers playing a major role in that. So in order to formally define this set of projected dynamics, so let me zoom in a little bit on the definition of this projection operator over here. So this pi of S, so S was the constraint set, f of x was the original vector field, and you see this operator has two arguments, right? So of course, let's say the original vector field is one, so a certain velocity, but it also depends directly on x, and the reason is that essentially we're going to project on the tangent cone, right? So the tangent cone of S and x, which basically define all the admissible velocities at a certain point. Right, so to make this a little bit more graphical, so what do we have here? So suppose we have here the state space, so let's say two-dimensional in this case. S is the constraint set, so the gray area. And if you are in a certain point x, so here at the boundary, then the tangent cone basically indicates all the admissible directions, so that's the red one and all the green ones and everything in between that are directions or velocities that keep us inside S. Right, so in principle at all times, we would like to have a velocity that is in the tangent cone of S at the current state. And what do we do at the moment? Of course, if fx is in the tangent cone, we don't have to do anything. But if it's not in the tangent cone, we correct for it by taking the closest point to fx inside the tangent cone. Right? So we do a sort of minimally invasive correction to make sure that we always are inside the tangent cone. And because of that, let's say using classical viability theory, let's say Aubin, Chelina, these kind of very classical works, you can then guarantee that all trajectories, if they exist, remain inside S. Okay, so this is a very powerful framework, but still it has certain limitations. So certainly if you want to move to let's say the use of these kind of projections in let's say closed loop systems with planned and controller states, then we have some limitations. So the first limitation is actually that the constraint sets S here, in order to make, let's say, the projection operator well-defined and also to have existence of solutions, so given an initial condition inside the constraint set, they typically require conditions like convexity of S or prox regularity. So we need some regularity of this set S, while if we are going to look later at certain applications in control, we are interested in constraint sets. So think about sector sets, which are very important in control, that do not fulfill or do not satisfy these properties of convexity or prox regularity. Right? So that means that many of the concepts, many of the basic fundamental questions have to be reiterated and have to be revisited and have to be seen if you can still prove, let's say, existence of solutions and completeness of solutions. A second and maybe more important limitation is that what you see here is that we have projection in all directions, right? So essentially we just take the closest one and there is no limitation on, let's say, the direction on which we project. Well, if you give this a little bit of thought in a, let's say, a planned controller configuration where we have planned states and controller states, of course, we can only apply projection to the controller side of things. So we cannot take, let's say, the planned states and change these by projection, right? Because they adhere to physical laws. I mean, we cannot just say, hey, let's project these, right? So only on the control side, let's say the cyber side of things, we can apply projection, which actually means that there is a restriction on the way we can project, right? So if x1 is a planned state, we cannot change that one by projection. But if x2 is a controller state, we can allow projection in that direction only, right? So instead of, let's say, full projection, we need some sort of partial projection with limited directions of projection that is possible. Right, so what does that mean? So let's take a closer look at this. So what this in fact means is, so of course, this was the original definition. So of course, we allow more irregular constraint sets, so sector-like sets. But what is more important, we will have to induce partial projection, since not all states are actually available for projection, which means that we have to extend this operator that we over here to a new projection operator that also includes a certain subspace that is a restriction on the possible, so on the admissible projection directions. So instead of having actually this projection operator, we're going to move, let's say, for closed loop control systems to this configuration, where we not only are looking for the closest vector in the tangent cone to the original vector field, but we put the additional restriction that the projection direction actually has to lie in this subspace, so this linear subspace calligraphic E, right? So that for instance could specify we're only allowed to project along the controller states. So to put this in a picture, right, it's the same picture as before. We're now change actually x1 and x2 here in planned states and controller states. So the same constraint set S, that's the gray area. So we have here the tangent cone again at this point. F of x in this case is pointing outside, so we cannot use the original dynamics, but we have to project it on the tangent cone. But so since not all directions are free, right, we cannot project as we did before in all directions, we have the restriction that somehow the projection should lie on this, let's say, shifted subspace, right? Because, I mean, we only can change XE. So basically, in this case, we have this as the projected, so the partially projected dynamics, right? So which is clearly different than in case we would allow full projection. Okay, so this is the real extension that we need. And then actually to make this a little more precise, although I feel I already hinted quite a bit on this. So this is particularly important if you start using, let's say, projected dynamics in a control context, right? Because in that case, what do we have? We have planned states. So XP is planned state, use the control input, and suppose the plan is given by this dynamics, and Y is a corresponding output that is available to the controller. And let's also assume for now that the controller is given also by an ordinary differential equation. So XC are controller states, Y is the input to the plant, and U is actually the controller output, so the control input, which in this case only depends on the controller states. So clearly, if we interconnect this, right, so we have X here as the combined plant and controller states by plugging the Y in here and the U equation in there, we get the unprojected closed loop dynamics X dot is F of X. So the ePDS that we now get, so the extended projected dynamical system that we now get, of course, the projection operator has to be, yeah, let's say this guy where this calligraphic E, the subspace that defines the projection direction is given by the image, so the column space of this matrix, right? So indicating we cannot change planned state, but we can only change controller states, right? So this being the identity matrix. So we can only apply projection here to make sure that planned states, or let's say the combined planned controller state, so X lies in a certain set S, right? So that's still up for us to define. And in fact, if you look at the literature, you see all sorts of variations. So in particular, if you have input constraints, right? So you want the U to satisfy certain input constraints, which can be very important, let's say in certain anti-windup schemes. So actually then the set S is given by all states X, for which actually this nonlinear expression lies in the input constraints at U. Right, so there's quite a bunch of papers that use this formalism, and actually this is quite nice to study, because somehow it's a little bit easier than the other case that I will discuss, because what we have here is that, of course, we only have constraints on XC, so on the controller states, and of course we have full projection, let's say, on the controller states, right? So on the level of the controller dynamics, you could still have a full projection, right? So the partial projection comes because we also have the plant states. Life gets a little bit more complicated if you have more complicated constraint set S, right? And that's the ones that we're going to use, particularly interested in this talk, is where the constraint set is not only defined in the controller state, but also depends on the plant states. And in particular, in this talk, we will be interested in the case where, let's say, the input-output pair of the controller, right? So YU, right? So expressed in terms of the states in this form, lies in a certain input-output constraint set, right? So IO is a certain input-output set that we are interested in, for instance, for using certain performance-enhancing benefits for the closed-loop system. So the latter is the particular one that we're interested in, but still we put down this general framework of ePDS, right? So we try to study it in generality, but many of the things were motivated, in fact, by constraint set that both involve plant and controller states. Okay, so this as a introduction to to the field of extended projected dynamical systems, right? And I motivated a little bit already why you need extension with respect to these classical PDSs. And now that we have laid down the groundwork, let's see what kind of projection-based controllers are particularly of interest, and in fact, other ones that motivated much of this work. So what we're going to do is we're going to indeed use these input-output sets that are sector-like sets, right, that many of us already know, right? And by choosing the sector right, we believe we can create improved input-output properties and improve performance, right? In fact, we're going to see how this can overcome, let's say, fundamental limitations of performance that are known if you stick to the paradigm of LTI control. Right, so the main motivation, right, that was driving us, let's say 5, 6, 7 years ago to start investigating in the use of projections in control systems, actually coming from a lot of high-tech systems that are very active around Eindhoven, so the Brainport Eindhoven region. So think about the ASML wafer scanners. So these are, let's say, crucial in the production of chips, right? So if you have one of you has an iPhone, right? So the chips in there are actually created by this machine. So just to give you an idea, and it's actually one of the biggest companies currently in Europe. And there's a lot of very fast and accurate motion, right, needed in these kind of systems, right? So many of the applications that I look into, so also here, let's say high-end printing systems. So think about Canon, OC, right? So they make very high-end printers where you need for production, right? So for high production, for high throughput, you need very fast moving motion systems. But on top of that, they need to be very accurate to actually give high quality. And the same holds, for instance, for these kind of systems. So these are a system that build printed circuit board, right? So pick and place machines. Same here, high speed, high accuracy is needed. And with that, we have to push the boundaries of our controllers really to the limits. So in order to control these systems, of course, feed forward is very important. So put it in gray here, right? So typically in these kind of controllers where we have certain set points that we give, that we want, for instance, certain motion stations to follow, let's say at high speed and with high accuracy. Feed forward is a crucial role in there, but of course also feedback to regulate or to actually to suppress disturbances that are always active on the plant, right? So to squeeze out these last important performance metrics that we actually need to satisfy. So if you look in the industry at the motion control side, what we typically see is that still LTI, so think about PID, loop shaping kind of techniques, are the real workhorse in industry, right? Because it's very effective It's very insightful, particularly because we have the whole frequency domain interpretation. I mean, it's even very easy to get, let's say, models of the plans by simple experiment, let's say, identification experiments. So you easily get an FRF, so let's say a Bode response, a Bode function of your plant, so non-parametric models, plus controllers that are also loop-shaped. I mean, it's a very convenient and very powerful and insightful design framework that is used a lot. However, what is also known is that if you have an LTI plant, right, so a plant that is well described by an LTI model, so a linear time-invariant model, and use LTI controllers, there are fundamental performance limitations, right? So think about the waterbed effect, so about Bode's gain phase relationship. So you have them in a frequency domain, but you also have them in a time domain. So for instance, what we know is that for certain plants, if you want to track a step response, let's say with zero steady state tracking error, so if you stick to the LTI paradigm, there's always overshoot in order to achieve that. Right, so you have a bunch of these kind of fundamental limitations, right? And in fact, they're very well documented in this quite well-known book. So fundamental limitation of filtering and control that describes also in the time domain all sorts of limitations that you have if you stick to LTI control. Right, so that's something you have to compromise. That's a compromise you have to make if you stick to this LTI powerful framework for design. It means you cannot squeeze out the performance to the maximum because of these fundamental limitations in the frequency domain, but also in the time domain. And just to illustrate this on, let's say, one of the key elements that is often used in these kind of controllers, which is a simple linear integrator, right? So for instance, if you want to track, let's say, step inputs or ramps, often you have to add a number of integrators to your controller in order to guarantee steady state tracking error of 0, or the capability to suppress constant disturbances, right? So integrators are a very important property for guaranteeing steady state error of 0 properties. However, a downside of introducing an integrator as well is that it introduces phase lag in your model or in your controller, right? So one of the things is already a little bit illustrated here, but I will explain a little bit better on the basis of this picture down here. But in principle, if you put an input, let's say a sign on an integrator, there is a 90-degree phase lag in the response, right? So somehow the feedback is too late, essentially. And this has, of course, major repercussions for let's say, in Bode's gain phase relationship, but also for overshoot, robustness properties, etc. So to show this a little bit, let's say, in the time domain, so I have a very simple graphic over here. So suppose this is a device, right, the motion stage, and we have to move, let's say, a mass or a wafer stage to a certain desired position very fast. And there's an integrator in the loop, right? So what is the integrator doing? So this is what you see over here. So initially, suppose there's a certain positioning error. So what the integrators are doing, starts integrating. So it starts integrating, and at some point the position error is 0, but now the integrator buffer has a certain positive value, right? So if you couple this back with a negative sign, that means there is a certain buffer accumulated at this point where the error, we are perfectly where we want, but still this integrator has this buffer which is going to cause overshoot, right? So it's going to drive us through the zero error point. Sorry, the zero error point. So it's going to push us through this point and causes overshoot, right? And then we first move forward, and then actually the buffer has to be emptied, so it has to be depleted, and then actually move back, and again overshoot, right? That causes the oscillations, and with that we get a very slow system, right? We get a slow system response, which means you feel there is something not right here. We are not squeezing out the maximal performance that we actually could have. And the reason is that you have phases of time where, for instance, the error is positive, but still the integrator is negative, right? So it's pushing essentially in the wrong direction. So there are moments of time when the integrator is really making things worse performance-wise. So the performance or the error is positive, and actually the integrator is pushing in the wrong direction. It makes even the error bigger for a while, simply because it's pushing in the wrong direction. So the sign of input and output are not equal. So one of the ideas that we had, and actually resembles some of the ideas that date back to the CLEC integrator, can we do something that makes sure that we always have the same sign of the input? So can we have integrators that have the same sign of the input as that of the output? So in other words, integrators that are never pushing in the wrong direction. And that's where projection comes in place, right? So in the CLEC integrator, right, so that date back to the 1950s, they did it by hard resets of the controller state. So by the integrator state. But that's a very nasty, or can be a very nasty, non-smooth operation, actually a discontinuous operation in your controller. And in fact, what you can do is you can achieve the same thing by simple projection, which is a way milder operation. And actually also makes the overall analysis easier. So let me see how this works out a bit, right? So suppose here we have this error, this positioning error, and here we have the control input, which in this case of an integrator is equal to the integrator state, right? So we zoom only in on the integrator, part of the controller in this discussion. So the simple idea is now that in principle we will follow an integrator dynamics, right? So omega h is here just some integrated frequency, just a certain constant. So E is the positioning error, xh is the buffer or the integrator state, and u is equal to, as I already mentioned, equal to this integrator state. And what I want to do by projection, I want to make sure that the sign of the input and the output is always the same. So in order to make this precise or a bit more specific, I always want to make sure that the input-output, so the error input pair always lies in a sector 0 to kh, right? So which is the gray area depicted over here. So that aligns between, let's say, the constant line, so the 0 line, and actually this line which has slope kh, right? Which is a tuning parameter for our controller. So in principle, we follow integrator dynamics, as indicated over here, but at the moment that the dynamics would drive us outside, so the integrator dynamics would drive us outside, we apply this projection, right? And again, we cannot change E, right? That's related to planned states. But we can project U, which is the which is the state of the controller. So we project it in such a way that we do not leave this sector. And with that, we always make sure that the input-output sign is equal. Right? And with that, you can immediately get interesting performance benefits. So this idea, right, so of using this projection to keep the integrator state or the integrator dynamics always active only in this sector range. If you do it explicitly, in fact, what you can get, you can write down the exact Higgs, right, which typically has integrator dynamics as long as certain conditions are true, and I will not go into full detail here. If certain conditions are true on E, U, and E dot, such that the vector field, so this dynamics keeps us inside of the sector. At the moment that, let's see, these conditions are not true, then essentially what we obtain is we need the projection to be active. And in that sense, what you can prove is that, so typically you have integrator dynamics, or you have a sort of gain mode, right? So actually, the dynamics is described by this algebraic equation. You can also take the derivative of this, so x dot is kh times E dot. But in principle, you are sliding or you're going over this boundary, right? In fact, projection on let's say, this boundary of the sector constraints actually will never happen because of the way the integrator dynamics work. So somehow, originally, when we introduced this projected integrator, without really knowing at that point that it was a projected integrator, to be honest, we call these systems hybrid integrator-gain system because it's hybrid, so it's switching between integrator dynamics. As long as we can follow integrator dynamics, we'll do it, but we switch to sort of a gain mode at the moment the integrator dynamics would drive us outside of the sector set. So this is another more explicit formulation, actually explicitly computing the right-hand side of this projection operator that gives you sort of a piecewise linear switching kind of controller for the control dynamics. And in fact, what is good to realize is that this controller only produces continuous, albeit non-smooth control signals, right? So reset controllers have discontinuous signals. This controller has continuous signals, which is quite beneficial for not exciting, let's say, higher order and model dynamic that you have present, possibly in a plant that you try to control. So just to put all of this into the this framework of ePDS. So how can we write closed loop Higgs systems as an ePDS? So take a look at this interconnection, right? So I've drawn here this picture a little bit differently. So suppose this is the plant, possibly containing linear parts of the controller, and we assume this part is described by this linear plant, right? So AG, BG, and CG are matrices of appropriate dimensions, and this is interconnected to the Higgs operator, so the Higgs controller, so this projected integrator. So clearly, the primary mode of operation of the Higgs is using this integrator dynamics, right? So in principle, we try to follow this mode of operation as much as we can, as long as it keeps us in the desirable constraint set. So basically, what we can do is we can combine this plus this guy to actually get a sort of unprojected closed loop integrator dynamics, right? So we just get this dynamics. And of course, what we want is we want to keep, let's say, the combination of E and U in a certain sector. So in this case, what we want is we want to keep so YU in a certain sector, or EU, right? So E over here, we want to keep this in a certain sector, right? So it's E here because actually for now we assume, let's say, a reference equal to 0. So actually the combination of Y and U or E and U should lie in this sector. So that's the constraint set. And we can only project, let's say, of course, along the Higgs state, so the projected integrator state. So that's why we get this E here, and we get this as the subspace of the projection space, right? So the directions of admissible directions, projection directions. So here are the integrator dynamics. This is X, the constraint set is given, and then we get this partial projection operator and these partial projected dynamics, so ePDS, describing indeed the Higgs controller in closed loop with a linear plan and possibly other linear control elements, fitting directly in this ePDS framework. So just to show you quite quickly why this is valuable before I go to a little bit of analysis for these systems, let's indeed show you that using Higgs elements, so with actually this quite interesting property that it always has the same input-output sign, that this can be used to overcome performance limitations that are known for LTI controllers. And one of these examples is actually, if you look at a configuration like this, so we have a plant here, so we have this feedback interconnection, we want to follow a reference. And in fact, what we want to do is we want to put a step on this, and we want to get that Y is tracking this step as fast as we can, preferably without overshoot, but have a steady state tracking error equal to 0. And what is known, so one of the performance limitations that's known for LTI controllers, that if the plant that we have, and it's given by this, if this has an open loop unstable pole, right? So in this case is something that we get, that no matter what you do, if you want to stabilize the closed loop system, steady state tracking error of 0, then you always have overshoot, right? So we designed a very good controller over here. Let's say that it has a linear integrator in there. So actually what happens is that you get the gray response, so you always have overshoot. Okay, so what you now can do is actually you can use this Higgs, this projected integrator, and combine it with, let's say, a certain pre-filter and a certain post-filter. So C2 is actually an integrator, and this is a PI type of controller that we used before the Higgs. And we see here the parameter of Higgs that we use, right? So we use the gain of the sector to be equal to 1, right? So we have the 0, 1 sector here, and we take this integrator frequency at first 8. And what you see is that actually the step response already has quite some lower overshoot, right? And a quicker settling time as a response. So it's way quicker, So it's way quicker at its desired position, right? With less overshoot. But if we actually make the omega even smaller, right? So 0.8, essentially what you see is that you can even avoid any overshoot at all while still having a tracking error equal to 0 in steady state, right? So, and this is something you cannot achieve with an LTI type of controller, no matter which one you pick, right? So what you see here is that we can accomplish by having a Higgs controller, right? Something simple as an integrator with a simple projection on it, you can overcome already these well-known limitations of LTI controllers. In fact, we have a few papers on this showing that indeed other well-known limitations of LTI controllers can be overcome by Higgs-based controller in the right configuration. Another thing, so just if you will buy next generations of iPhones, basically the chips in there are produced by wafer scanners that have Higgs in the control loop. So don't tell this, our secret. So basically Higgs controllers are already used for improving performance. And we did first experiments, but they're already out there, which just really shows also the power and interest of industry in these kind of controllers. And what I really like is on the one hand, this let's say this industrial relevance. So people are really interested from an industry side, but there's also real cool mathematics and system theoretic questions to be answered as far as fundamental questions about existence, completeness of solutions, stability, incremental stability, etc. Right? But in principle, we tested these already, let's say, in real industrial settings, and I will not go into detail here, but if you look at the position errors compared to, let's say, the state-of-the-art controllers that they're always using, you add Higgs to it in a proper configuration, you see you get way smaller errors and also quite a quicker settling time, which means improved accuracy, positioning accuracy, and improved throughput. Right? So that immediately is very valuable to, of course, the operation of these kind of machines. Okay, so as I already hinted upon, is industrial relevant, but also cool math, right? So studying ePDS, which is a new class of dynamical systems, is of course very attractive and very appealing, and actually keeps us busy. So that makes us quite here in Eindhoven quite excited about this class of controllers and ePDS in general. So let me show a few of these more theoretical analyses or analytical results that we have. So starting with existence and completeness of solutions for ePDS, tailored to these projected type of controllers on sectors. And then I will go to stability analysis. And later I will also show you a little bit on incremental stability properties and convergence properties, as this is a nice property you want to have, I think, for any controlled system. So as I said, so if we start looking at a new class of dynamical systems, so ePDS, or these closed-loop Higgs systems, we have to prove again existence of solutions. So given an initial condition, given an external input, does there exist a closed-loop solution? And preferably, of course, it should also be complete so that it's defined for all times t from 0 to infinity. So in particular here, I focus on this class of ePDS that are induced by, right, so of this form where we have, let's say, constraints at S on the states that keep the input-output, or the output-input in this case, or the input-output of the controller, which is, of course, the output-input of the system, in a certain K1, K2 sector, right? So you cannot fully see it, but so in principle, this is the line K1Y, and this is the line V is K2Y, right? So the area in between these lines, that's the sector that we're interested in. So we already saw that if you have plans, let's say plan states XP, and this is the plan dynamics, input U. I assume here that by a proper coordinate transform in this model, we can write Y as a linear combination of the states. The controller is also a dynamical controller, where I assume that actually also by proper coordinate transformation, you can make the controller output, so the input to the plant, a linear combination of the controller states. And then, of course, as before, we can write the closed loop dynamics X, so consisting of XP and XC in this unprojected vector field. So what we actually get here is that the overall constraint set is actually given by, so X, so all X's for which the Y and the U, right? So this guy and this guy together lie in this sector K1, K2. Okay? Right, and of course we can only project controller state, so that means that actually the projection directions are in this cartographic E space, which is the the column space for the image of this matrix over here. So if we have this configuration, right, incorporating, amongst other, these closed loop Higgs systems, and we assume Fp and Fc to be continuous, so the plant dynamics, unprojected plant dynamics is continuous and Fc is continuous, then we can prove that for any initial condition that starts inside S, there exists, at least on some time window, non-trivial time window 0 to t, there exists a Caradere type solution, so an absolutely continuous solution to this ePDS, so to this closed loop, let's say, projected control system. So moreover, we can prove completeness of solutions, so that the solution exists for all times, if we have a linear growth assumption on the original unprojected vector field, right? So of this type, so there exists a constant m, such that the norm of f is actually bounded by this affine expression of the norm of the state. In fact, we can show that, and that's where actually these linear equations come in, that this affine growth condition can be translated also to the right-hand side of the ePDS. Right, so in that case, we have completeness and solutions. Moreover, if you add external inputs to it, disturbances, references that are piecewise continuous and bounded, we can show these exact same results. Right, so showing that indeed the fundamental property of existence and completeness is typically satisfied by ePDS under these conditions. Right, so in this paper, we consider more classes of ePDS for which we study the existence and completeness of Caradere solution to ePDS. So it's a quite recent paper, was also presented at the CDC. Okay, a few words on stability analysis, and maybe I already revealed a possible direction to go, is because I already hinted upon the fact that if you have a projected integrator, particularly if you have sector constraints or for instance, polyhedral constraints and the dynamics is linear, you can write down the explicit formula for the projection operator, and typically this is a discontinuous piecewise linear mapping, right? So it's a discontinuous piecewise linear vector field that you obtain, right? And because of that, you can, in closed loop, if you couple that, for instance, to a linear plant, and maybe other linear controller elements, at the end of the day, what you get is a closed loop system that is a discontinuous piecewise linear model, right? So it's piecewise linear and can be expressed. So we have all sorts of linear models that are active in a certain region of the overall state space. Okay, and if you have this, of course, then we could start applying maybe standard let's say technologies or methodologies, for instance, constructing piecewise quadratic Lyapunov function for these kind of piecewise linear dynamics. So what is important in this case to realize, what makes it a little bit more exciting, is that some of these dynamics live on lower dimensional, let's say, facets of the constraint set. Right, so often what you see is that for piecewise linear systems, certainly in continuous time, the discontinuity can play a role. So you want to make sure you also have certain robustness properties, for instance, by considering Krasovsky regularization. So that's one thing that's guaranteed by the result I'm going to give you on the next slide. But in particular, you have to incorporate that you have some of the linear dynamics, so some of the modes living on lower dimensional subspaces. So in fact, what we did, and don't try to read in full detail this result on the right-hand side, but what you typically can do is you can partition the state space in certain conical regions, and that's what we did. Define a quadratic Lyapunov function for each of the regions, make sure it's continuous over the boundaries in the right way, and make sure that you have a certain decay condition on this piecewise quadratic continuous Lyapunov function. Right, preferably for the Krasovsky regularization and to have also certain inherent robustness properties. And in fact, so if you do this, right, so you try to synthesize such a piecewise quadratic Lyapunov function, right, so it's written over here, you can write down an appropriate set of LMIs that, if these are feasible, that you guarantee indeed the system to be input to state stable, right? So we get input to state stability of the overall system. And of course, you can play with how refined you actually will make this partitioning, right? And maybe you can also choose in which direction you partition. Maybe you partition only in the E direction, maybe only in the U or in the E and the U direction. Maybe involve the E dot direction as well, or maybe the full state space, right? Of course, at the cost of having more computations. So this is one approach, right? So following an LMI, piecewise quadratic Lyapunov function approach to certify stability or input to state stability. Another one that we are particularly interested in is motivated by this interest or this strong LTI loop shaping frequency domain controller design framework that is very powerful and actually loved in industrial practice, right? So having the previous tools, actually what they require is a parametric state space model, which is not always easy to get in industrial practice, while it's often quite easy, right, by using multi-sign experiments, but also by using quite basic identification techniques to get a frequency response model, so a body plot of your plant system, right? And it's nice if you can only assess stability or certain properties based on an FRF, so frequency response function of the plant, which is easily to be obtained. Right, so the question that arises is, can we analyze these kind of configurations, right? So linear plant and maybe linear control elements, for which we have an FRF, right? Easily measured by simple identification experiments. So can we say something by using FRFs only, so only frequency domain data, on the interconnection with a hybrid controller like HIGS? Right, so that's why we want to get somehow frequency domain guarantees, so not LMIs. We want to get frequency domain conditions for checking stability of such a configuration. So of course, underneath this linear plan, there is, let's say, a certain linear state space model, right? So given like this, and this is interconnected with the HIGS over here. And what we can prove is that this system is input to state stable, right? So with respect to the remaining input W, references, disturbances, etc. If, let's say, the linear part of the system is asymptotically stable, right? And also that's something you can test by using Nyquist type reasoning, let's say on the FRF of the plant. So we assume this part of the system to be stable itself. And then the only condition or a sufficient condition to guarantee stability is that if you indeed look at the transfer function of the FRF of this plant, that in fact this satisfies this condition. Right, so it satisfies that the real part of the FRF of the plant actually is bigger than -1/kh. So in principle, the Nyquist plot, right? In fact, I think I have a picture. Let me put it here. So in principle, you draw the transfer function in the frequency domain. So the Nyquist plot, you draw it, and it has to be to the right of this line -1/k, where k is of course the tuning knob that we have in our that's the tuning knob that we have in our controller, right? Describing the sector. Right, so we need nominal stability plus this frequency domain condition, which of course reminds of the circle criteria. Right, so and why is this very important? Because now this is something we can test using measured frequency response data of the nominal system only, and we have a sort of graphical check, right? And also, right, so this check that I just give you, I mean, we can check, so we can check if it holds or not. Plus, it gives you information when it's not valid, right? So if you violate it, at least you know which frequency range you violated, and you can do possibly a reshaping of the plant in that region, right? By adding maybe extra controller elements. So it gives a direction for redesign, while LMIs only tell you, well, it's yes feasible, you did well, but if it's not feasible, there's no hint, no direction, also no robustness margin whatsoever, and so no hints on how to redesign the overall control. Right, so that's the benefit if you can do it in a frequency domain form, and that's having our attention effect to improve these results quite a bit. Right, so a challenge here, because this of course looks like a Leroy type interconnection, but of course remind me that let me remind you that in the circle criterion, these have to be static memoryless elements in case you want to apply the circle criterion. Right, so in this case, of course, this is a dynamic element, right? So of course you can be inspired by let's say the circle criterion, but you really need to add certain extra ingredients in order to prove this result. Right, a short example. Right, so what do we have here? We have a mass, right? So just a double integrator. So just a mass being shifted around. We have a low pass filter over here. So this is a low pass with PD. And so we have this configuration. We have HIGS actually added in this configuration with the two control parameters, which is the K, the sector that describes the sector, and the omega that describes the integrator frequency. So that involves the internal dynamics of the HIGS. And what did we do? We studied the stability of this closed loop system. So first by extensive simulations, and that revealed to us that actually the gray area, so in the parameters K, I hope you can read it. So this is the K of the controller and the omega of the HIGS controller. So for these parameters, so this was the white area was unstable, the gray area was stable. Right. So and of course these are quite accurate based on extensive simulations. You can get a good insight. So what did we do here? So the dots are related to where we could get the LMIs feasible using a single quadratic Lyapunov function, but as procedure relaxations. So you see, you can fill quite a bit of the region already if you do use a piecewise quadratic Lyapunov function with a 2D partitioning. So basically only partitioning in the E and the U direction. Right, so just a local partitioning, let's say, of a two-dimensional subspace of the controller. So then we already get very close to the boundary. And if you do a 3D piece of quadratic Lyapunov function, where also use the E dot direction, where we, let's say, use a very fine partition, you see we can fill the whole region up to the boundary. Right, but of course at the price of having way more extensive computations compared to just using a single quadratic Lyapunov function. Right, so the complexity of the LMIs grows quite quickly. Just to compare this to the frequency domain condition that we had. So you see the red dashed line. So with that one, we can only prove the stability to the left for points to the left of this line. So you see it's quite conservative. So compared to the LMI condition, but of course it's way more insightful. Right? So it's quite conservative, but I mean, it has certain benefits for redesign and also given an indication of robustness, at least how far you're away from violating the check you have to do in case of this circle criterion-like condition. So we're still looking into less conservative conditions, frequency domain. So frequency domain conditions that are less conservative. So a few years ago we had one result. We keep on working just to see how can we use, just based on ever the plant, guarantee stability in this setting. Okay, so to shortly get to an end here. So what did we see so far in this first part? So I introduced HIGS, so projected integrators, as a big motivator behind the full study of these extended ePDS, so these extended projected dynamical systems. Closed loop HIGS are ePDS. I showed you a little bit how they can overcome fundamental limitations. So yeah, let's say these PDSs are these projected controllers can be very powerful, right? So simply adding it can already give big performance benefits, overcoming fundamental limitations, but also being very useful in practical applications, as I showed you, with a few simulate or experimental results with wafer scanners. We discussed existence and completeness of solutions and two ways of verifying stability of these kind of systems. So the last theoretical part that I want to mention is incremental stability and convergence, right? So we somehow want that all solutions converge to each other, right? Which is a very beneficial property that you want to have for typically closed loop systems, right? So it indicates also certain non-sensitivity to initial conditions. But importantly, often incremental stability can be used to prove convergence. And with that, you have unique steady state solutions. Let's say unique bounded steady state solutions. So for instance, if you put a periodic solution on the system, you get a unique periodic steady state solution out to which all the other trajectories converge. Right? So just like a stable linear system, sign in is a unique steady state sign out of the same frequency. Right? So if you have, let's say, somewhat stronger incremental stability properties, so input to state incremental stability or exponential incremental, you get the convergence property that guarantees the existence of a unique steady state solution that is incrementally stable. And if you have those, you can start thinking about having non-linear Bode plots. right? So just as we have the Bode plots or the FRFs for closed loop systems that give a lot of insight in performance, you can also have that if you have the incremental stability, the right incremental stability properties, you can also have these kind of properties for nonlinear closed loop systems. Right, so that's what we're after, because this is very powerful in steady state performance quantification. So in general, when you look at the, let's say, a general nonlinear system, and you put a bounded periodic input on it, it is not, so for a general nonlinear system, it's not guaranteed there is a unique steady state response, right? In fact, you can have multiple equilibria, or you can have multiple responses, and depending on initial condition, you go either to one of those equilibria, to one of these these steady state responses. However, if you have a property like incremental input to state stability, right, which is defined over here, then you, so for the nonlinear system, then you have guaranteed there is, if you put a bounded periodic input on the system, that there is a unique periodic bounded steady state response of the system. So a unique one, which is periodic with the same period as the original one. Right, so in fact, the property that we're after is incremental input to state stability of the nonlinear system, which tells you that if you take two different inputs, so W prime and W2, we consider two different initial conditions, and you look at the response of the system, right, for these two different initial conditions and two different inputs. So this is the response of the system at time t. That if you look at the difference, then this is upper bounded by a term that is going to 0. So beta is a KL function, right? So this is related to the difference in initial conditions and vanishing when time goes to infinity, plus a term that is related to the difference. So the L infinity norm of the difference between W prime and, so W prime and W double prime, right? So in case you apply the same initial condition or the same input for both scenarios, for both initial conditions, so then this term is of course 0, this disappears. So then we see that basically for the same input, all trajectories converge to each other as time goes to infinity. And if they're not equal, I mean, a certain term is remaining that is related to the size of the difference in W prime and W double prime. Right, and these kind, if you can prove this condition, we also know that a periodic input on the system gives me a unique steady state output of the same period. So the way we analyze this, again, we look at this configuration. So linear plant over here, so given by a model of this type, so linear plant and possibly also linear control elements, so in interconnection with Higgs, right? So we have this guy over here. And we now look at a class of controllers that is a little bit more general than the Higgs, in the sense that, so this hybrid controller over here, I mean, we can have, so XH is still a scalar, but what we assume here, so we still will project on a sector, but we are not only allowing, let's say, integrator dynamics, but this can be a general non-linear dynamics over here, right? So depending on plant state and the input to the Higgs. Right, so in case this is integrator dynamics, this F is just equal to Z, right, to its inputs. Right, then you have Higgs, but we allow this more generality. So in particularly, sometimes we're interested in first order projection elements, as we call them, where this F is just some linear dynamics. Right, so again, alpha 0 brings us back to the original X, but also nonlinear Fs are possible. So one way that we proved convergence or incremental stability, which in case, let me emphasize again, we're talking here about a discontinuous dynamical system, a discontinuous peaceful linear system. So this is quite a tough job. So in principle, what we did here is we started studying the incremental dynamics, right? We have a first order projection element here. That is the unprojected dynamics of the Higgs. We look at the incremental dynamics between two solutions, right? So we look at the delta X dynamics. And in principle, what we try to do is directly construct a Lyapunov function, and in fact an incremental Lyapunov function for these incremental dynamics. Right, so in fact what we try to do is by smart design, by looking at certain particular properties of these incremental dynamics, we could design directly a piecewise quadratic incremental Lyapunov function certifying incremental global exponential stability and this input to state convergence property, if certain conditions, certain LMI conditions are actually true, right, involving the controller parameters, kh and omega h, and other types of variables. Right, but these are LMIs, and if these are feasible, we can guarantee for that controller configuration, we can actually prove the input to state convergence. So the input to state stability and the input to state convergence property, giving us for periodic inputs unique, globally asymptotically stable periodic steady state responses. Another approach that we recently obtained was using a little bit of a more modular approach, a small gain, so an incremental small gain type of approach, where again, same configuration, G a linear plant, which we assume to be stable now, right? And since it's linear, so since it's an asymptotically stable plant, we know this is also incrementally, exponentially stable, and input, incrementally input to state stable. So in fact, we can show that on the increments. So for the linear part, we have such a an incremental input to states property, right? Where delta U is the difference in the inputs to the plant, and delta Z is the difference or the increment of the output of the plants. Then, plus we can prove, right? So for first order projection elements, so with this dynamics, we can prove that the first order projection element is incrementally input to state stable. Right, and we can actually explicitly and actually quite tight compute in this case the gain the incremental ISS gain that we have. So both for the linear part as for the Higgs or for the FOPE, so the first order projection element part. And then, of course, if you assume that the non-incremental system is input to state stable, the boundedness of trajectories, plus we have the incremental small gain condition, we can prove that the interconnection is actually incrementally input to state stable. Right, so now following a somewhat different approach, so not a direct approach, but a small gain approach, which is more modular. Just to illustrate this, why this is of interest to us, so we took here, let's say, a linear plant. So this is the transfer function of this linear plant. We took here H to be a first order projection element with this dynamics, and we indeed could establish using the tools that I just showed you that this closed loop configuration is indeed incrementally input to state stable. And with that, if you know that we put now an external periodic signal on this closed loop configuration, we know there's going to be a unique steady state solution, and all the other solutions converge to that one. And in fact, this is also a periodic steady state solution of the same period as the input. Right, so that's what we see here. So we see here the response of Y. So for different initial conditions where we start, you see these gray ones, but everything converges at the end to the same solution. And this is what the control input is doing, so the integrator output. So you actually see here also nice periodic behavior, and all the other, so irrespective of the initial condition, we converge there. And you see indeed the same period as we have for the input. And you indeed see it's periodic, but it's not a sign, right? So you see here it's quite funky behavior. And with that, of course, we can do this for all sorts of inputs of different frequencies. We can compute then the corresponding steady state solution, and we can start drawing characteristics of this, right? So as a function of the frequency of excitation, right? So if you put this periodic solution on this, for instance, we can look at what is the amplification of the energy, let's say the ratio between input and output as a function of the frequency. So we could plot this one where we really compute, let's say, the steady state response Y corresponding to this input, and we know that's now unique. Right? If it's not unique, now you have multiple ones, you don't know which one to plot. And this actually leads then as a function of frequency, for instance, about, let's say, in these kind of amplification diagrams, right? So root mean square ratios as a function of the input frequency, which of course give a lot of insights in where the system, in which frequency ranges the system is sensitive, so the closed loop system, and which ones is not, right? And these are typically the kind of, let's say, diagrams, graphical insights that are really appreciated by people in industry. Right, so that actually solves or more or less addresses the first part. So as I said, I've little time for the second part, so I'm just going to throw this at you. But just to summarize, so I hope I convince you about the use of projection-based controllers. right? By, for instance, playing with these input-output properties, making the input-output sign the same. We studied fundamental questions of existence, completeness of solutions. I gave you various ways of doing stability. Plus, we also looked at incremental stability properties and convergence properties to guarantee actually nice performance, steady-state performance assessments also for these kind of systems that are, let's say, Bode-like. So we get some sort of nonlinear Bode plots, which are quite appreciated by industrial. So the second part, as I said, I'm going to give you a sort of crash course here. So I'm going to just skim over it to give you the main idea. I don't know if it's useful. I hope you get also a little bit excited and discuss with me how we can use this idea. But I want to use projection to change the dissipativity properties of, let's say, an unprojected controller. So I take a controller, put a smart projection around it, and then induce certain nice properties. So the main motivation why we started doing this is if you have a plant and a controller. So of course, a well-known result is that if the plant is passive and the controller is passive, the interconnection is passive, and asymptote it's Lyapunov stable. If one of them is strictly passive, you even can get under detectability conditions, you even get to asymptotic stability. Right? Or if you have a certain gain here and a certain gain here, you have a small gain. Right, that's a certain other dissipativity property, then you know the configuration under a small condition is stable as well. So what we now want to do is, so we have a plant with a certain dissipativity property, can be passive, strictly output passive, can be a small gain, right? So we know that this has a certain gain property. How can we take a controller and put a smart projection around this, such that we are sure that the closed loop configuration is actually stable. Right, so that's the idea. So you put a stupid controller, but we're just putting a smart projection around it. You make sure that still the closed loop system is stable. So sort of a stability shield, if you will. So you can put quite aggressive, maybe unstable controllers there, but by just simply projecting, you make sure the closed loop is stable. Right, and the way is by introducing the right dissipativity properties into the controller by proper projection. So the idea, so we have some plant dynamics, which has a certain passivity property, so a certain dissipativity property, so a quadratic supply rate. So as said, we assume detectability here. We just take a pretty random controller, right, which has a controller state. So the first controller state is the output after proper change of coordinates. And we have some other controller states. And of course, we can put the plant and the controller state together to get the unprojected closed loop dynamics. So what we now want to do is we want to add a projection to the controller on a certain sector, a K1, K2 sector, to make sure that the input-output of the controller, with that of the plant, lie in a certain sector. And we make sure that the sector is going to be tailored to the dissipativity property of the plant. In particular, if the plant satisfies a certain QSR property, think about passivity. Actually, that's the one I have over here. So in that case, we have Q0, R0 as is 0.5. So we get that the plant is passive. So in that case, maybe let's look at this case. If I just take this sector, so making sure that K1 and K2 are both positive, so that means the sector is contained in the first and the third quadrant, then that's a design condition I can pick. So I take random controller dynamics. I just put this sector around it that lies in the first and the third quadrant. I know the system is going to be stable. How wonderful is that? Irrespective of what the controller dynamics is doing. Right, so the same applies if you have an output strict plant, a finite L2 gain, right? So if you know that the plant has a finite L2 gain of gamma, then if I choose the K1 and the K2 like this, so the sector, which I can just induce because I'm the designer of the controller, between -1 over gamma and 1 over gamma, then in principle I know whatever the controller dynamics is, the closed loop is stable. Right, so this is formalized in this result. Right, so essentially, if the sector design condition holds that I just indicated, so the original plan is QSR dissipative, passive, strict output, passive, small gain. You do a proper sector design. We need, if you also want to have internal stability of the controller, we need a certain ISS condition on the other controller states that do not appear directly in the controller output. Because of time, I'm not going to dwell too long on this. But if you do this design properly and the plan is detectable, we have global asymptotic stability of all solutions of the closed loop system. Right? Just by clever projection. Dummy dynamics, dummy controller dynamics, but just putting the right sector around this controller will do the job. Right, so I don't have too much time, so sorry for that, for taking a little bit longer today. But I think it could be a nice idea, but it's an open question to you. How can we do this, right? So how can we exploit this idea? It's quite funky. So for instance, here we have a passive plant. It's a detectable dynamic, so it's linear. We put this controller. I mean, actually, if you don't do projection and destabilize the plant, we go here bananas, we go to infinity. But if you just project on this sector, we just simply stabilize the plant and we get nice responses. Right? So it's a very easy way of actually designing passivity-based controllers, where somehow the internal controller dynamics are free. So maybe for some applications this is useful. And in fact, the nice thing is that you can use quite aggressive controllers, right? And by projection, you preserve safety and stability. Hey, it's time to wrap up. So again, apologies for being a little bit late. So what did I do today? I introduced the class of extended projected dynamical systems, so ePDS, because we needed them for studying projector-based controllers, where we want to use projections to change the input-output properties of the plant. So we studied existence and completeness of solutions to these ePDS, and I showed you how these projection-based controllers, so these that change the input-output properties, can be used, one, for changing or guaranteeing sign equivalence of input and output of controllers, which is very useful for overcoming fundamental limitations of LTI control. Right, so in the frequency domain and in the time domain, for instance, no overshoot, where any LTI controller would overshoot with a simple Higgs. So projected integrator, you can already overcome this. I also showed you there's quite a few experimental, so industrial successes of this. I showed you one of them in wafer scanners. So your next iPhone is made by Higgs. I showed you tools to do stability analysis, both using LMIs and frequency domain conditions, right, where we have a strong, let's say, ambition to work on these frequency domain conditions, because they're very useful for redesign of controllers and design of controllers, and give robustness indication and match industrial practice. We studied incremental stability and convergence via two different approaches: a direct one, a direct piecewise quadratic incremental Lyapunov function design when certain LMIs are satisfied, or a small gain type of approach as a first start of working with nonlinear Bode plots for steady-state performance specifications. And basically, I just, and I realized this was way too quick, but I also showed you by just adding a projection operator to a rather random controller dynamics, you give that controller certain dissipativity properties. For instance, induce certain passivity properties, such that the connection with a passive plant is always stable. Right? Somehow I feel this can be useful, but I think we have to explore this further. Future work, study extended projected dynamical systems as a class of itself, and it's linked to other classes of hybrid systems. For instance, the classical PDS or oblique PDS. Stability analysis, we want to get less conservative conditions, particularly in frequency domain. Discrete time and sample data Higgs, right? At the end, we have to, let's say, implement them in a sample data or digital setting, which requires, let's say, discretization of these kind of controllers. Multiple Higgs. So what if you have multi-input, multi-output with many channels, you having multiple Higgs there? I mean, then the LMIs can blow up quickly. So how can we analyze still, let's say, using this in a scalable way, maybe exploiting ideas from networked or networked systems? So another thing that I worked on, but only worked at the end of the day for convex constraint sets, is if the original dynamics unprojected satisfies a certain incremental stability property, can we have that inherited by the projected dynamics? Right, so I have some results on that, but as I said, only for convex constraint sets, hence not for the sector set. So we cannot do that, because then it would be nice, because you have to only guarantee incremental stability properties or monotonicity properties for the unprojected dynamics, which is smooth, instead of for the projected non-smooth dynamics. We're also looking into the relationship between projected dynamical systems and control barrier functions. Right, so basically, on the one hand, this can shed a light on the study of control barrier functions, because you can look at the limit case of PDS, but otherwise you can also, other way around, you can use it for projected controllers and projected dynamical systems to be approximated or implemented by controller your barrier function-based controllers, right? So this is, I mean, I'm very happy with this very recent result. I think we just in the beginning there. Applications is important, also database learning and tuning of projected-based controllers, right? So using data, but also online learning and improving the parameters of PBC, also when the plant is shifting, that you adjust your controller online. So with that, I want to acknowledge the great work of these people. I cited their papers on the way. So it was not just me doing all the work, it was really a team effort. And I also want to thank ESC, so the European Research Council, for supporting part of this work. And with that, I thank you for your attention.